Good morning, this is Ankush Chakrabarty. I'm a research scientist at Mitsubishi Electric Research Labs, and today I'm going to present some work on simulation failure robust Bayesian optimization for estimating model parameters in black box models. This is joint work with Scott Bortoff and Chris Laughman.
Advances in modeling and computation have resulted in high-fidelity digital models in a wide range of industrial and engineering systems that are capable of simulating the dynamics. However, not all of these models are necessarily have closed-form analytical representation, so they may be software-based or analytical forms may not be accessible due to proprietary reasons. Furthermore, they may be quite slow to simulate if they're doing a really high-resolution or high-fidelity replication of the true system dynamics. The key step is model calibration in order to make these high-fidelity models indeed high-fidelity or more reflective of the true system dynamics. Typically, model calibration involves the estimation of a set of parameters of the simulation model so that the predictions of the model are close to the observations that we're seeing from the system. And because the simulations are slow, we need these to be efficient. And because there are no closed form representations all the time, we need data-driven mechanisms for calibration. And one such mechanism that's become popular recently because of data and sample efficiency is Bayesian optimization. In most formulations, iteratively solve an optimization problem through repeated simulations in the calibration context. So parameters are typically adjusted and then the model is evaluated via simulation, and eventually we minimize sub-model fit or calibration cost. And an assumption throughout the literature is that the model can be simulated forward in time over any duration of interest for any set of parameters within an admissible search domain. However, we will see that this is not always true. Attempts to simulate these models for certain parameter values can result either in massive simulation time or complete failure in many cases. One typically does not know for which sets of parameters these failures will occur, especially because we assume that closed forms are not available to us in black box type models. And this happens in a lot of domains, especially in space cooling or energy systems, where the simulation models are usually software-based, such as in Modelka, and have widely separated timescales. For example, buildings have very different timescales from HVAC units. There are hybrid dynamics, and there are nonlinear interactions between these different physical systems. So one doesn't really know what is a domain where the model will successfully simulate in the parameter space. So rather than identifying which parameter sets will result in successful simulations, the more common practice is to completely ignore the information conveyed by a failed simulation and to just rerun the simulation and try again. And of course, as you can understand, this will result in significant wasted computational effort and time and slow down the convergence of any calibration algorithm quite a bit. So the objective of this work is to try to optimize the model parameters via calibration without attempting too many simulations that are likely to result in failure. And this will have the effect of improving convergence of the calibration and reduce the amount of total computation time and effort. This is a typical workflow of how to use Bayesian optimization for model calibration in a data-driven manner. Just to understand that we have a goal, which is to compute this optimal set of parameters, theta star, that minimizes a given calibration cost function. And the calibration cost function is usually defined or known as a function of the model error, that is the difference between the measured data and the model outputs. But typically, we do not know the map from a parameter set to this cost function. So that map is unknown. We assume that we can have simulation models that can generate outputs which are the same as the measurable outputs of the true system. For example, temperatures in HVAC systems or building systems. And we have a known admissible set of parameters. So we have a search space we can search over, but we don't necessarily need a well-known distribution over these parameters. Just ranges are enough. And this figure shows you a schematic of how this works. So we have a true system, which is throwing out measured data. We have a model, which is parameterized by theta, which also throws out the same simulation outputs. And therefore, we can compute a calibration cost based on the discrepancy between the true data and the observed and the simulated outputs. So since we do not map, the parameter to cost map is unknown. We use Gaussian process regression in order to get a mean prediction of that map, as well as uncertainty quantified around it. And the uncertainty informs through the use of acquisition functions where we should sample the parameter space next. And typically after multiple iterations of this cycle, we will end up with a good set of parameters that results in a low cost function. In our work, we assume that failures can occur after a set of parameters are selected within some unknown failure region, which is a subset of capital theta, that is our search space. So in such a situation, if we assume that the optimal set of parameters are not in the failure region, that is, the optimal set will result in successful simulations, then we propose failure robust Bayesian optimization, which can learn from simulation failures to understand where the failure region is and how to avoid it so that we can optimize the calibration cost without wasting computational resources. This is a schematic diagram of how this works. So we'll start from the bottom right, where we have the same setup as classical Bayesian, a simulation model and observed data. We can compute a calibration cost function and use GPs, that is the parameter to cost regressor, in order to come up with the mean and variance of that calibration cost map over the entire admissible parameter space. And we have the acquisition function. So you've seen this all before in the previous slide. What's new here is we have a simulation failure label. That is, once you pick a theta and you simulate the model up to duration t, is it resulting in a successful simulation or not? Accordingly, we can classify or we can label as +1 or -1, and we can set up a failure classifier whose job is to estimate likelihoods of simulation success and failure. That is, indirectly, it's learning what theta f looks like. So the combination of the acquisition function and the failure classifier is this proposed failure robust acquisition function, whose job is to incorporate the probability of simulation failure and bias the next candidate it selects to be outside of what it has learned of the failure region, theta f. In this way, by iterating over and over, we're not only getting to an optimum in the sense of the calibration problem, but actually a feasible optimum. That is an optimum that is likely not to fail. And therefore, we're reducing the amount of computational wastage as we're doing this Bayesian optimization with FRBO. In order to perform FRBO, we need to do some data collection. Essentially, what happens is, since the admissible parameter space theta is known, we can sample a set of, say, theta 0 to j from it, and we can simulate the model. And if the simulation is successful, we can compute the scalar cost function j from 0 to j. If not, we replace this cost with some nonsense value like NAN. And also for each simulation, we can see whether or not there was a simulation failure and label as +1 or -1 accordingly. And therefore, learning the failure region can be posed as a classification problem for the next step. In particular, we use a scalable variational Gaussian process classifier as the failure classifier. That is the classifier that learns the failure region. Essentially, we do so because it assigns a probability failure to any parameter in the search space, and it allows representation of complex decision boundaries via the use of kernel functions. So with the dataset DJ that we discussed, we set a Gaussian prior at the observed parameter sets, and we choose our kernel function, and we use the Squashing-Bernoulli distribution to obtain the joint distributions of labels and features. And in order to improve scalability, we use inducing points. All of these details are in the paper. And we use a variational elbow loss for learning. And in order to reduce the sample complexity of the learning classifier, we use an entropy-based active learning methodology. A key step in coming up with good parameter candidates iteratively in Bayesian optimization is through the use of acquisition functions. And these are typically easy to compute functions based on, for example, the mean and the covariance of the Gaussian process. And the maximum of such a function, for example, here, I put down the expected improvement acquisition function, whose maximum is going to be where the best parameter candidate is given the observed data so far. Now, in FRBO, we incorporate the probability of failure directly into the acquisition function. And this is why we call it a failure robust acquisition function. So for example, we propose the failure robust version of the expected improvement, which is a multiplication of the expected improvement, as well as 1 minus the probability of failure. So by picking a particular sample that maximizes this failure robust acquisition function, we're actually saying that the higher the probability of success, the higher chance that this particular candidate would be selected. as long as respecting the expected improvement, we are going to get something that is likely to be a minimizer of the overall calibration cost function. To validate the proposed FRBO scheme, we're testing on a stiff nonlinear set of ODEs of chemical kinetics known as the Robertson system, where we hide the true parameters and we try to estimate them in about 1,000 FRBO iterations. The ground truth is obtained by simulating using a stiff solver for about 20 seconds. And we have a huge parameter search space. So from 10 to the minus 3 to 10 to the minus 1, 10 to the 2 to 12, 10 to the 5 to 15. So massive search space we're searching over. And the test set is also from 10 to the minus 5 to 10 to the 5. So a large test region, quite much larger than our training data test time range. These are the different sort of hyperparameters we're using for the variational Gaussian process classifier and the GP, and all of this is implemented in PyTorch. And an interesting thing is that since we don't expect the estimate of the failure region to change too much from data point to data point, the failure classifier doesn't have to be retrained at every sample. In fact, here we trained it for about the first 300 data points that FRBO collected, and then we skipped every 100. So we only trained it 7 more times. As you can see from the central figure, the final model is very well calibrated. You can hardly see any difference between the predicted and observed trajectories over this large time range, and the RMSE is very small. And in the bottom right here, we've taken slices of the failure region, and you can see that the failure region boundaries are not just linear. So different slices indicate that these are actually quite curved, and therefore this motivates the need for advanced nonlinear classifiers like VGPC in order to estimate these kinds of regions. We compare FRBO with some standard heuristics and other algorithms that are used for calibration. The first is ZRBO, which is essentially skipping any calibration cost function that results in failure. So we just ignore that data and we try again. High BO is when the simulation failure cost is replaced with a very high value to discourage the BO algorithm from searching in those spaces, because clearly if you set a very high value of cost, even if it's a fake value, you're encouraging it to understand that there's no minimizer there, so you avoid those regions. And of course, the final is MCMC methods or Monte Carlo sampling methods, which are very common in, for example, building calibration literature. So we show from the top left plot that the FRBO learns this failure region within about 300 active learning iterations. And after that, there are 2 interesting things. So from iteration 300 onwards, you see no further red vertical lines, which means there are no further simulation failures. The FRBO only encourages exploration in regions outside of the failure region. And because of that, the convergence of the algorithm to the optimal parameter set is much faster than any of the competitors out here. To summarize, we realized that simulation software is designed and validated over a limited region of an available parameter space. And we may not know a very good set of bounds on this parameter space since we assume black boxness of these models. So the regions over which the simulations will fail are rarely going to be known during downstream design. Calibrating a model for different data sets requires exploring the parameter space and could involve trying parameters that will eventually result in simulation failures. So to avoid wasting time and due to successive simulation failures, we'll provide a new methodology called failure robust Bayesian optimization, which is a methodology for black box model calibration that involves learning the failure region with classification methods and incorporating that information into an acquisition function of a Bayesian optimization procedure. This results in reduced wasted simulation time and computations, as well as improving optimal speed. Thank you for listening.